Good afternoon, class. In today's video, what I'd like to do is to start a series of videos on rotational motion. Now, a lot of you might be thinking at this point, well, don't I already know a bunch about motion? I mean, we've studied linear motion for basically the whole first part of the year. So why would rotational motion require its own series of videos? And the answer to that, quite simply, is because linear motion, while very important and very useful in our modern society, actually is not what makes us a modern society. It's our exploitation of and usage of rotational motion as well. Some examples are your car tires. The fact that you have a car that even moves because there are pistons that fire, there are axles that rotate, there are tires that turn, that are able to give you basically the freedom to move around, whether you're here on Oahu or whether you're somewhere in the rest of the United States, the mainland, or elsewhere out in the world. The fact that you can move using a car is actually really important, and that's where angular motion comes in. So we're going to be exploring that in these next series of videos. So what I thought I'd do is to introduce it and to really understand the weirdness, I would say, of angular motion, or rotational motion, I should say, is to compare and contrast some of the equations that we dealt with in linear motion and find their analog in rotational motion. Also, for those of you who are athletes, you will also be interested in this whole concept of rotational motion because this is actually the science of injuries. This is actually where you get injured. I'll give you an example. In football, unless you get hit in the head, if you take a shot to the body, like somebody tackles you and hits you straight in the body, most likely you're not going to get hurt from that, or I should say injured. Of course it'll hurt, but you'll never get injured from that kind of a collision, basically. It's when you fall to the ground, that you slap into the ground like that, and that rotation, that is what causes the injuries. And so it would be important for you to figure out where you can, what you can do to minimize some such injuries. So let's talk about this. What are some of the similarities and differences between linear motion and rotational motion? So with linear motion, we have distance, velocity, acceleration, momentum, and force. All of those things are the same in rotational motion as well. However, how they are built looks different between one and the other. So let's start with linear motion. We start with distance. X equals velocity times time, which sounds great. However, if you want the angular or the rotational equivalent of that, it's going to be arc length, S, is equal to the radius of the object times the angle, or theta, of that the object has gone through. So whatever this distance is when you curve like this, that arc that it made, that's how you find that distance. Well, already we've got something different here, and hopefully you're noticing as you've taken a chance to look at this R value will start to show up in more places than one, which kind of gives you an idea of what that looks like. Next we have velocity, v equals distance over time, or acceleration times time, and that's wonderful. That's something we've studied since the beginning of the school year. However, velocity in rotational motion looks like this. This, I know some of you are going to say, that looks like a W. Actually, it's not. It's the Greek letter omega, lowercase, of course. The uppercase value is the unit for ohms. That's uppercase omega. This is lowercase omega. This angular velocity is going to be equal to the angle that the object rotated through over time. So looks fairly similar to velocity, but also a little bit different. Now we move on to acceleration. Acceleration is velocity divided by time, which is kind of the same as angular acceleration, except that it's the Greek letter alpha, which is equal to omega over time, so we have some similarities there, and that's not too bad. Then we have momentum. In linear motion, it's P equals mv, or mass times velocity. So the equivalent of that, or the analog in rotation, is that angular momentum, L, is equal to the moment of inertia times the angular velocity. So that kind of makes sense. Now, of course, immediately some of you might be thinking, what's the moment of inertia? Wait, I know there's inertia, but what's moment of inertia? And so that's where we have to get to that towards the end, because that is actually one of the big differences between rotational motion and linear motion. So let's move on to force. So we use our famous equation, F equals ma, which is Newton's second law, and that's wonderful. However, in rotational motion, you've got a force, but the thing is that has a unique name. It's called torque. And a lot of you, especially if you're in auto mechanics, you probably have heard that a lot, especially because it deals with the engine and the forces of the engine, which you would call the torque of the engine. That is given by the equation tau, the Greek letter tau equals R times F, which is this force that we find over here. R is the lever arm, or the length of the lever arm of whatever it is that's applying that torque. One thing that I do want to point out is that, especially for all you more advanced math people, you'll probably note that this is actually not a complete equation, because this tau value is supposed to be a vector. This force is supposed to be a vector as well. And so it really should be the components of that vector that I should be writing down, which would be, so you might want to say it's like tau equals RF sine theta, because it's a cross product. And you know what? I agree with you. However, I am trying to make this video more for the basic level of physics, so that's why I have that basic level of torque in terms of this equation. So now we do have to come to the part where I am going to move off of the comparisons are kind of done over here for linear motion and rotational motion. This moment of inertia, this is exactly where we kind of go off, not really off into the deep end, but it's also where I have to, I take a little bit of a dive away from traditional textbooks, okay? And I wanted to point this out because the moment of inertia is analogous to the mass. Mass is defined by Newton's first law, says that any object that has mass will resist a change in its motion. So if it's going, it'll keep going. If it's stopped, it will resist even starting. So that's mass, and that's regular inertia. The moment of inertia is basically an object's resistance to rotation. So, which you can imagine from watching basically any tractor pulling something. If the tractor is pulling, let's say, like in those traditional plows that you had from like the 1600s, those things were very heavy pieces of metal. They would sink into the ground and they would plow or push apart, cut up the dirt as they would go through the field. However, if you put it in a wheel, let's say, it will actually still be able to continuously cut through the dirt and maybe break it up as you need to, but it will do so more efficiently because you don't have to worry about it getting caught on anything like stones or other things that could, make the plow less efficient, maybe stop, and it would get caught on like a clod of dirt or something like that. So we do need to talk about the moment of inertia and how things resist that change in motion. Unfortunately, this is where I also depart a little bit from textbooks, because textbooks would tell you that the moment of inertia which is I, is equal just to mr squared, or so mass times the lever arm squared. I put this star in here on purpose, okay? This is where it's basically my note to you that tells you, hey, you have to take this into account. There's a thing you need to take into account, and that thing is a geometric factor. So let me give you an example using this ruler. For me to rotate this ruler, like so, is fairly simple when I hold the middle of it. However, if I hold the end of it to move it with that same amount of force, it moves a lot slower. And so that's why I have to make sure that I am purposeful in putting this star in there, because that star is a geometric factor. And that's actually what I'm showing you with this. When I do this, that has a different geometric factor than if I grabbed right here in the middle and just did this. So I wanted to point that out, and the reason why is because you have to look this up. This star value is found in a table. You can Google search it if you want to. You can look it up in any textbook, and they'll tell you various or general geometric factors for these moments of inertia. But you have to know that they're there. You have to know to look for them. Otherwise, you're going to just assume that it's one, and that's not necessarily correct. For example, if you took a solid sphere, generally speaking, which is like the Earth, you would have to use 2/5 instead of 1. So you have to know that kind of stuff to be able to put it in. That's why I depart from most textbooks and most other people who teach physics, because I say that I need to put this in here. Will you see this outside of Mr. Chu's physics class? No. Will you see this outside of this text, my notes, or any textbook that you would even have? No. This star is exactly what it is. It's something that I invented, that I stuck in here just to remind you that that you need to take care of that geometric factor and don't forget it, because that is definitely something that's going to come back and lead you to wrong answers when you're doing some of the homework. So just want to point that out. I will be bringing back that meter stick, because it will be important when we talk about all of these different things, because if you notice, distance, force, and the moment of inertia all had that R value in there, which is a lever arm. And so I thought I'd point that out and highlight the differences between linear motion and rotational motion, and give you an idea of what we're looking for in terms of this series, and hopefully also a few insights into how to not only apply it academically to your homework, but also apply it to your everyday life, because this is the science of injuries in sports especially. So keep that in mind. Good luck in your studies. I'll see you in the next video.